the left here, the little pink graph thing, that is the GraphQL logo. Logo on the right, hopefully you all can hear it. That is the Rust logo. Today we're going to be talking about, what is the GraphQL compiler, kind of the challenges and the things behind, how to build it basically, and then kind of what were the features of Rust. I hinted a little bit of this before, but it was first written in JavaScript. What prompted us to switch over to Rust? What are the benefits of writing in Rust, and like kind of how does this all fit together, specifically within the Facebook architecture for the GraphQL native compiler. So, a little bit of background about myself. My name is Nikhil Handyal. I'm a software engineer at Facebook New York. I work on the GraphQL native compiler. I've been on the same team for about 3.5, almost 4 years now. I joined the company back in January of 2018. And so, yeah, about 3.25 years. It's been great. I had a lot of fun with it. And so, yeah, let's get into it. So before we kind of get into the nits and grits, GraphQL is it's kind of something different, and so I wanted to take a little bit of time to go over kind of the basics of what GraphQL is, what is it, kind of why do we care, how does it be relevant to this talk. And so a little quick poll for the audience. How many of you guys know what GraphQL is or have heard of it? Oh, damn, let's go. Quite a few of you. I am very impressed. Okay, that is awesome. For those of you who don't know what GraphQL is, you can think of it as like a query language. It's a way for you to query the data that you want. It's specific. It's kind of like SQL, but it's structured more to like a graph, and so it's very tree-like hard, how you query data. It was developed by Facebook a few years ago to kind of help us, efficiently query their graph and also send data back. So it's a query language, and it's also a response format. There's GraphQL server, there's GraphQL client, might use like execute query, get the response, and a lot of other stuff. Here is a quick kind of example of a GraphQL query, like what you can expect the response to be. So over there on the left, we have a really simple query, just called my query, and kind of like SQL, where you like select blah from this table or whatnot. You just kind of have this structure. There's different like keys and kind of like objects, nested objects and arrays and things like that. And you can just be like, there is a property called me that's available on the top level thing. I want you to select the first name, the address, which is also an object, and their city and the state, and that's the structure of your query on the left. And then you can kind of see here on the right, the response mirrors that structure pretty verbatim, and then you just kind of fill in the fields that you've asked for. And so under the me object, the first name has been resolved to my name, which is Nikhil, and the address is New York, which is where I live, and the state is also New York. And so pretty simple. I think it's pretty cool. And yeah, this is kind of basic GraphQL. The next thing kind of I want to touch on before we move on is this notion of like composability in GraphQL, right? There's little building blocks that we have called fragments, and they allow you to take very large queries and split them up into smaller pieces. You can kind of think of it as a function within a query. Not really, but it's a way to kind of name little portions of your query and then reference that in other places. And so here we've kind of taken the example we had before, and we've just kind of split it up into this thing, which is an address fragment, which kind of just selects the fields that were originally in address, and just kind of move them out into address fragment, and they're kind of independent. And we see the response here is exactly the same as we had before. So just kind of like real quick, this is what it looked like before. That was the response, and now we've gone into this like fragment thing, and we notice we're just doing ... address fragment, and the response is the same. So it's really just kind of a thing on the query side. And so, I forgot your name. What's your name again?
Marcus.
Marcus. So Marcus, a few minutes ago, asked very nicely, what is a compiler, right? And so, for GraphQL, what the native compiler does is we take in this source code on the left, right? We take in query, my query, all these fragments, all these different things. And when I say native compiler, that means it has to run for our iOS and Android apps. And so neither of those languages, like Java and the Objective-C runtimes, they don't know how to understand this, right? I can go type this in and be like, what is this? Like, what am I supposed to do with it? And so what we need to do is we need to translate all of this stuff into Java classes, Objective-C classes, and that is then what is the programming API that developers will use within the company. They're like, I want to fetch these fields, right? They'll be like, get first name, this or that. And so here we have just kind of a quick example of what our Android models look like, or kind of a really basic interpretation of how they could look like. Right? You have your query, my query, same stuff that we had as before on the left. And this is just kind of the interface that we would generate out of it. We would parse all that into the AST, and then at the end of it, we generate this stuff here. And one thing that I do want to draw attention to, because it's going to be very important as we kind of go into like what were the problems with the data compiler to begin with, kind of why did we transition out of JavaScript, why did we transition into Rust and things like that, is the way that we implement this spread operator. So if you kind of notice, right, we do address fragment, and over here, this is kind of the interesting part. So we look at my query, we look at the interface address that kind of returns to you this block of data that you would get from like the address of selection. You notice that here it implements address fragment and all this other stuff, and then you have kind of duplicated fields left and right. The way that we kind of looked at, we decided to model the spread operator, like what the dots are called, is through basically inlining. You take all the fields in the fragment, you would inline it into the parent selection set, and you would generate, the model like this. Yeah.
Does everything go down to string, or are there other data types?
So you can define actually in the Graphql schema your own primitive data types, but the ones that are kind of defined in the specification are, I think, number, string, arrays, like strings and numbers and objects. And is there another date, I believe? Oh, and booleans and enums.
It's floats and ints, it's not numbers.
Floats and ints, okay. Floats, ints, strings, booleans, enums, and then arrays and objects of those entities. And then you can also define custom primitives, and then you can also define custom objects on the server schema as well. Any other questions before we kind of move on? They are, yeah. So I'm glossing over a lot of the server side, kind of the server side type schema. And so there are, within GraphQL, the language, we natively support interfaces, unions, objects. An interface is just like an interface in any other language. It's kind of like a set of common fields. A union is like it's a disjoint kind of, it's like a distinct between one of a specific set number of types. And then an object is like a standard object. You can implement an interface and you can define its own fields and like the return types and things like that.
Can you talk a little bit about the parser used to generate, like the parser used to parse the thing on the left?
Yeah. So the parser we actually have is we originally had it in JavaScript. That was like the reference implementation of the GraphQL like reference spec. And so we had the AST, all the types, the parser, and all that stuff was in JavaScript. A lot of work was done by the Relay team. Robert, huge shout out to you guys. They rewrote the parser in Rust. It's been about like 18 months-ish by now. And so there is now a new reference implementation, Relay, kind of the parser in Rust. And we have, just kind of all the basics that you require to like traverse the language. So you have like the AST nodes. From the AST node, we actually have like another level called like an IR node, which is there's one set of validation that's like done on the AST node. It will link basically your client like queries with like the server types and things like that. And so it's a little easier to use than just having like the raw AST and the raw schema and trying to like link everything yourself. The language like primitives, the language tools will kind of do that for you. An example here could be like, you'll have a node for first name, and then be like, what is the schema type that references? Before, you would have to kind of do that manually. Now there's like actually a method on like that AST node to like give me the schema type, and I can just go straight to it. And so that kind of linking is what the IR does, which is something we didn't have in the JavaScript implementation. So the Rust one's very cool. I think it was a lot of fun to work with. And so there is a link for it a little later, which I can kind of show you guys. To let you see kind of like the Rust parser implementation for like the GraphQL source code and things like that. But yeah, any other questions? Yeah.
So is this all immutable data, or do you mutate the data on the back?
The query, or
like, is there a mutating query, or is there only?
There are, yeah. So this is only like a get. So this is immutable. GraphQL also has instead of a query top level object, there's a thing called a mutation top level object. And that is what you would have to define the mutation on the server, and that's what you use to actually change the server data types. But here, yeah, like this is considered like I didn't put it in immutable so that you can just execute this any number of times and you should always get the same result given the same inputs. Yeah, nothing should change on just a query. And any other questions? Cool, okay. So yeah, the thing I just really wanted to stress here was that the way that we represented the spread operator for the fragments in GraphQL was through an interface here. And so we had like your return type of the address field actually implemented the address fragment interface. And through that, in Java code and in Objective-C, we actually took all these values and basically inlined them up and up. And so these models would kind of, it just basically looks as if that fragment never existed on the GraphQL side, because you can just call it get city, get state. So just remember that. And so now, what are the limitations with what we were doing there, right? And so the big thing here is it's non-modular, right? And so when we first kind of wrote GraphQL and kind of were working with it, we're like, yeah, cool. Just one giant kind of like repo of GraphQL queries, no notion of a library. Like we can see everything when we have like the compiler will look at all the source files when we have to make a change. And that became very, very slow, very, very fast. I don't actually know how, it was a couple of years before I joined, but by the time I joined the team, it was pretty slow. And so that's when we were starting to think about what is the next generation architecture for the native compiler. And so the global view to regenerate models, thousands of generated changes for a single GraphQL change, slow GraphQL plus Java compilation times, and then kind of a technical detail of the Java runtime is that we had degraded runtime performance because of the way that we, if we look back here, to the way that you have to implement and kind of how the Java class loader looks at all the interfaces and things like that. If you have a very long fragment hierarchy, you can have hundreds of interfaces that you have to load at the very beginning. You have thousands of fields. And that became a pretty big, measurable performance regression, an improvement that we could make by kind of shifting to a more modular architecture, which I'll get to in a second. But yeah, so these things require global views, 1,000 generated changes for a single GraphQL change, slow Java GQL and Java compilation times. Just to kind of illustrate on why that's a problem here is, so if I were to take address fragment over there, and if I were to remove the state field, what happens, right? I have to then change the definition of this interface. I then need to know that this interface implements it. I have to go change the definition of that. If this goes on through a very large tree, and that's referenced in hundreds of thousands of different queries, you will have thousands and thousands of generated changes that are just invalidated by just making that one small change in GraphQL. And so that kind of illustrates to you why it's not modular, why you need to view the entire world, kind of have to see the entire GraphQL fragment hierarchy, how everything's laid out, how you have many changes, and then just looking at everything the GraphQL compiler slip, and then also the thousands of changes that makes the Java compilation, the subsequent compilation of Java code also very slow. And so that's the issues that we had. And again, all this stuff was written in JavaScript, and so it was just generally slow to begin with.
The projector wasn't written in that.
Did that projector went out?
That's part of Rust.
Any questions while we deal with technical difficulties? Marcus?
Is the parser recursive?
The parser isn't recursive. What do you mean?
So I know that Rust has a physical limit of how long or how far you can recurse down, and I'm wondering if the implement the ...
Yeah.
if that's implemented recursively to find all of them and then put them back in place.
It is not, no, it's more like a map. And so we'll do that's kind of where the AST and the IR happen. So we'll do one parse on the AST, and there's a restriction in GraphQL where definitions seem to be globally unique, right? And so we'll parse all of your, let's say a foo fragment, R fragment, SAR fragment, or whatever. They will all get parsed into a map, right? And they're all keyed. And when we do the IR, that's what we'll kind of display them. And so you don't need to actually go through the recursive structure to find the entire hierarchy. Just kind of waiting. Yeah?
If you have different layers that have the same name, like if you have a state, underneath it would be, working, sleeping, drinking, and also a state on an address for the US state, or is once you use that phrase, is it sort of global nature?
Yeah, keys, you can kind of think of it as like a path. It has to be like unique. But yeah, you can have keys at the same level. Keys at different levels can have the same name. So you can have like an address that defines a state field, and then I could also have like I don't know, a city, some other object somewhere else that defines the same field as well. Any? It just kind of stopped working. Yeah,
Nice in person. These human moments.
Awesome. Okay, cool. So Marcus asks, is the parser recursive? No, it's not. We actually use like a map to kind of parse all the objects into it. Alright, cool. Yeah, so Marcus asked about the, is the parser recursive? It is not. We parse everything into a map first, and then we link everything afterwards. And then, yeah, gonna continue unless we, any other questions? Alright, cool. Okay, cool. So this is kind of like the big change that we shifted to kind of help with the big modularity problem that I was talking about earlier, right? And so the big thing to notice, right, here, same query, names, fragment, all the stuff, same stuff on the left, but we've changed this here. The address interface no longer implements the address fragment. And we kind of, instead of interpreting the spread operator as like an inlining operation, we kind of look at it as a pointer now. We kind of like follow the data tree from one node to another. And so here now, instead of implementing the address fragment, we just kind of have this address fragment method call that kind of will then just shift us over to the address fragment, and then you can query the data like that. And so here's a quick model comparison, left and right. Left was the old one, right is the new one. We can kind of see the difference here, right? So the one method we have here on the right is the as, kind of the following from one node to the other. And then on the left side over there, it's we just inline all the fields that we're selecting to begin with. And so this, yeah, kind of here, this is how we broke our huge kind of dependency chain on having to view the entire world. How we can just look at one section of the code, one library, one module as it's called, to generate your models and kind of not have to do everything. That would make the only requires the view of one library to regenerate your models. The generated changes are proportional now to your GraphQL changes. You have a fast Java compiler, and you have fast Java compilation as well. And like I mentioned, you no longer have this huge Java interface inheritance, and so your runtime performance has also improved as well. And so is that all kind of evident, I guess, from the models, how the new ones allow us to do that and the old ones don't? Cool. So now we're actually in a good spot. So we've now gotten to a point where our new compiler, the new compiler architecture is incremental, right? It's like one library, one module. It doesn't have to look at everything. And now we have to implement it. And so this is kind of where Rust, we considered it for a very long time. We wrote all this stuff in JavaScript to begin with, and we ported it over to Rust at a later point. But the architecture stayed the same between our Rust implementation and JavaScript. And so I'm just going to talk about this stuff and ignore the JavaScript kind of headache that we went through, and we'll just talk about how it's all built on Rust right now. And so one of the things that is kind of unique, I think, to the way our compiler works is that it is actually built on top of another build system, another build toolchain. And so that's what Buck is. Have any of you guys heard of Buck or Blaze at Google? Cool. So it's kind of like, I guess it's similar in a way to a lot of the other build tools. Kind of like what you have in JavaScript is Grunt, and then you have like Groovy for Android. It's another kind of modular build system. Buck is the one that it's very heavily predicated on Blaze, which is what Google built. It is the internal build system that all the mobile builds and Facebook use. And the Graphql compiler is actually heavily built on top of Buck. The way that our system works actually is that we have our you can think of it as like a compiler. There's like a compiler binary per library, and then we basically tell Buck, hey, when you need to regenerate GraphQL sources, call this binary, and then we define a bunch of inputs in like the Buck build graph. Developers will do that. But Buck is doing a lot of the orchestration for us behind the scenes to get everything to run. And so, a little quick, little addition on Buck. One of the things that one of the big things that it influenced our architecture is that compiler binary that I was talking about is single threaded. There's just one single thread that just generates the sources for one specific library. And the reason we chose to do that is actually because we rely on Buck to parallelize everything. And so Buck, has the entire view of the build graph, and every Java library for an Android app is like, hey, these are the GraphQL sources, we need these models generated. Buck will then figure out how to structure all of those into the different levels, and then it will parallelize everything. So it'll spin up 15 instances of our compiler, and then we'll just single thread it through each one, but we're still getting the parallelization benefits through Buck. And we didn't want to deal with all of that because one, it made our code a lot easier to write and maintain. And it was also kind of, the value proposition at that point was very low, right? Because to generate one Java model class is very, very fast. And so the overhead of actually spinning up new threads, of kind of all of that headache was just not worth it. And so we just decided to write it single threaded and let Buck deal with all that stuff. And so quick little side of there is just an example of how you would write like a Buck library, right? You have the name of your library here. It's defined as like an FB Java library, and then you have the name of it. You've defined what are the Java sources, what are the GraphQL sources, and what is the dependency hierarchy for that library. And then on the right, this is basically the output. We take that step, and behind the scenes, there's a bunch of other, as Buck goes through to evaluate the build graph and come up with the final dependency graph, it is actually, there's code that's being executed while it generates what this thing called the action graph is. And we attach a bunch of rules and a bunch of code that runs during the graph evaluation phase. And the output from all that is this manifest that comes into the compiler. And that tells us what is the root node that we are trying to build, what are the actual source files, what is the actual file, what is the hash of that file, so on and so forth, what are the dependencies of that specific GraphQL library, and then that blob is kind of replicated over and over for the entire dependency graph. And this is the input to the compiler, and then we'll take all the source files, we'll parse them into the ASTs, the IRs, and then we'll do our validation classes on it, we'll do some internal transformations on them, and then the ultimate output that we get is the model files are an example of it, but we also have kind of enums that we generate, different types of models, and a bunch of other artifacts that are relevant as well. And that was just kind of an example of showing you how Buck will actually parallelize a bunch of different things that it has to do. So there you can kind of see it had to build I don't know, like 10 or 12 different rules, and kind of it's just doing them all at the same time. And that's something that we don't have to do. We just let Buck do that internally. Fun fact, Buck is also being rewritten in Rust at Facebook, so a lot of Rust adoption at the company. Cool. So yeah, what do we have to build? This is kind of you made some changes in developer. You're like, cool man, I want to get my models. How do we actually get everything to work? We ask Material, what are the changed GraphQL source files? Then we ask Buck, hey, go tell me all of the libraries that those source files belong to. And then we say Buck build on all of those targets. And that is actually how we invoke the compiler. We're not actually calling the compiler directly. You're not calling like Java C and specifying a bunch of different things like you would with the Java compiler. We do have our own command line like interface into that, but under the hood, we're just calling out the Buck for majority of things. Cool. Any questions so far, or to this point?
Why was it faster to do these Buck rules in Rust than Node?
Well, Node itself is just super slow. Yeah, I think the startup time on Node was that alone. By the time Node even began executing our first line of code, was like 10, 15 seconds. How do I call it? The bundle, like the JavaScript bundle, was like absolutely huge. And the way that we had to manage all the dependencies, how do I put this? The dependency management system is also through Buck, and Buck tries to aggressively cache all those dependencies on your local machine, but if you have like a cache miss and have to go download those dependencies from somewhere, those dependencies, as many of you know about the Node modules, is just huge, and so it takes forever to like bring that up to your machine. And it's like fine if you're trying to run like a server, it's like you have to allocate the startup cost, but we don't want you to be waiting for like a couple minutes for your models to be generated. And so yeah, just like the JavaScript dependency management, like the huge bundle size, like Node would have to go through and parse all the JavaScript source code. Just the startup cost was like very slow. And then some of the assets too. So like the GraphQL schema, the GraphQL ASTs, once they were parsed into Node, those took up tremendous amounts of memory. And so we actually got to a point where we were consuming 5-6 gigabytes per invocation of the compiler on a developer's machine, and we would basically crash some of our CI machines. We're like, oh, it's like just not enough memory on this. We have to like up those limits, and so it was just a very, very resource intensive operation in JavaScript. And Rust is just orders of magnitude better in all those regards. So yeah, that's one of the reasons. Yeah, we switched over to Rust as well. Decided to ditch JavaScript.
So, I guess that question I had earlier about what the kind of use case is. I think you answered it with that question. Is the turnaround time is in a developer's environment as they're morphing models to develop a new feature?
Yeah,
that's the critical path.
Yeah. And so one of the metrics that we try to optimize is kind of developer iteration speed, right? Like what is the time it takes between making a GraphQL change and being able to use that change in like your product code, or time to kind of when you actually like build the app and use it. And the GraphQL compiler is very early in that phase, right? Because you have to declare, it's basically your data model. You're declaring what are the fields and what is the data that my product can use. And then while you're trying to like, I don't know, it's like as a developer, hey, I need this field. Like, oh, I need this field. You like realize you take these in, you take these out, and the compiler was taking like 2-3 minutes, like it was in the beginning. That was just like very, very slow, right? And so now we've actually gotten down to a point where it's about like 5 seconds, so it's like much faster. I don't know the percentage went on that, but you can see after 3 minutes, it's like 5. And so, yeah, but that is the path. Kind of the flow is the developer will write their GraphQL model or modify their model. The query, the models will then be updated, and then they'll go write their product code to actually consume those models.
Do you have to answer to like the Facebook developer experience police or anything along those lines? Or?
We work closely with them, and GraphQL kind of the compiler speed has been a point of contention for folks. And so yeah, it's
what do they call it? Is it called the developer experience police, or is there?
Yeah, we have there's DevX for different I guess words, but ours is like the mobile DevX experience, and they run a survey every half, and we've been on it plenty of times. And so yeah, it's something, not even that, right? Like I think what's it called? The modularity change that we made to actually improve the runtime performance, that was actually the runtime and the Java compilation time as well, because that not only impacted a GraphQL developer, but that would pose, just overall compilation times for people. And so the Buck team was not very happy with us for that one. They're like, yo man, we did it. And just ruled us in general, they'd be like, make a GraphQL change and what, wait like 30 minutes for, because I think all of FB4A, like the Facebook for Android app, if we build everything locally, would take upwards of an hour. And so a lot of things, Buck will cache a lot of things, right? If it doesn't rebuild it, you're like, hey, all these nodes, there are no changes. I can just go download it from the remote cache and then use those artifacts and be good to go. And we were just invalidating, 25%, 30% of the Buck cache, and for like a single change. And so that was a huge problem. So yeah, just kind of going over a few things that I mentioned earlier. The native compiler is single-threaded. It's just one process per library. We let Buck handle all the parallelizations. It is built on top of the Rust relay primitives, the relay Rust primitives, sorry. So that's the Graphql parser, the AST structs, the IR, which stands for internal representation, and there's like validation rules and kind of the traversals for the AST as well, kind of visitors and transformation kind of foundational like elements. That is the link to the repository, Facebook, github.com/Facebook relay, and the treatment compiler. And then kind of these two little bullets here at the bottom, the validation paths, kind of the way that we separated the compiler into two phases of execution. One was like a validation phase, and then one was like an execution phase. And so this was kind of, it helped frame the way that we surfaced errors to the user. And so what we do in the validation paths is, that's basically when we go through, we parse all the AST, the GraphQL sources, the ASTs and whatnot, and we're trying to figure out, like, is this, can be valid GraphQL, but it can be also invalid kind of based on the structure, the constraints that we've placed on the system as well. And so we'll do a bunch of validation and be like, hey, I don't know, you're trying to fetch this field and this, or you named a fragment called bar, and that fragment is also, named bar somewhere else. You can't do that. And then these are basically all like user fixable errors, right? And so you want to get basically everything done in like that validation pass. And this is also like the pre-transform. We do a lot of transformations in the Graphql compiler. We take, just as like a nicety for developers, you just write certain things and then we'll kind of expand that into like a different selection set or a kind of shorthand that you can write and we'll expand it into something else, or we'll automatically insert fields that we expect you to always query for, but there's just a lot of work to repeatedly do it, so we'll just put that in there for you. So we'll do a lot of pre-transform validation as well. And if any errors kind of come up at this point, we'll then surface them to the user. And we're trying to get to a point, this is something hopefully we can look at kind of towards the end of the year, going to the next year as well. It's like looking at the Rust compiler as like a prior art to get really good error messaging and be like, hey, you're trying to do this, that's not correct, you need to do this instead, or like go change it on this line and do something else instead.
Have you considered reaching out to Esteban, who's the Rust compiler error magician?
No, haven't, but definitely will do that. Okay. Is Esteban on Facebook or?
What?
Is Esteban on Facebook?
No, he works for us. But
Okay. Yeah.
it's reachable other means.
Definitely.
Definitely great. And
yeah.
yes, the answers are really good, and what they've done is been amazing. So following our models the right way.
Definitely. I was mentioning to someone, I think at the beginning of the talk, yeah, that is one of my favorite features of the Rust compiler itself, is just the way that they handle error messages. Absolutely fantastic. So yeah, if we can do that as well for the Graphql compiler, would absolutely love to do that. But yeah, so we do the validation pass, and then we get down to like basically execution, right? Now it's like, how do we actually, we're just generating, the actual, the source code, the generated code. Everything at this point is expected to work. And if something doesn't work at this point, it's kind of like a compiler internal error. We basically just dump out and panic and just we'll put an error message to the user to kind of like, hey man, reach out to us on the team and be like, this happened. But it's not something that we expect the user to fix on their own. But really, kind of our reliability metric that we kind of go for is to make sure that execution pass will always complete, right? It's not, like it doesn't fail due to compiler failures, it fails due to user errors. And then we want the internals to just always work. And so that's a little bit of how we phase like the two portions of the execution. And then, cool. So,
The question is that?
hang on, yeah, someone had a question?
Yeah, so are there any sort of optimization passes, and how does the user control, if there are, how does the user control which optimizations to use?
Yeah, so we, in the native compiler, don't do that many optimization passes for like our models and our queries. I know Relay does significantly more than we do. And Relay, just for context, is like the JavaScript GraphQL compiler. You write GraphQL and they transpile it into JavaScript models that you can use in your JavaScript code. But we do some, but not a lot.
It's not optimizations, it's like what is necessary to get the Java to understand the data coming back from the server in a way that Java can like iterate a class out of it. So it's not like, we don't have the concept of like performance optimizations, although Relay actually does, where Relay will compress queries so that the server executes those queries faster. I believe our team has basically outsourced that work to the server. So when we send our query text to the server, we expect the server to do those optimizations for us. Because we're lazy.
But yeah, like some of the, I think some of the cool stuff that Relay can do is they can look for like duplicated selected fields across multiple fragments, and they can be like, hey, you're asking for redundant data, we don't need this, and so we're just not going to fetch this block of data. It's less work for the server to fetch it, because you just need it once, so why evaluate for it twice? But I am not an expert on all the stuff that they do, so I will leave it at that. But yeah, one of the cool features that I wanted to talk about, kind of in conclusion here, is this thing called our flat buffer schema. And so one of the really kind of expensive parts, right? We mentioned that Buck starts one process per library, and one of the really expensive things that we have to do, even in Rust, is to parse the entire schema, right? And the basic schema is absolutely humongous. I don't know, like in terms of gigabytes how big it is, or megabytes. It's very, very big. Large enough to a point where VS Code would not open it, so it is a huge file. And I believe, I mean, we kind of see some time to it plot. It took us about 5.5 seconds, and then after I talked about this optimization, it took us half the time. And so, if you're doing this this very expensive operation repeatedly across multiple invocations, that's going to add up, even if you're doing all of them at the same time. And so, what we did is, you guys know what flat buffers? You guys heard of flat buffers? You've heard of us? Okay. And so. Basically what it is, it's kind of like a indexed array, right? You can define like a schema for like the fields and the data that it contains, and it's just one lookup into these values. And so we have a pre-built step that creates this like GraphQL flat buffer schema. And so then we basically don't need to parse raw GraphQL text. We just take this huge block of memory that we know represents our schema, and then just immediately start like querying it for data. Because the schema really, as far as we're concerned, is just kind of a giant database of types, right? We need to know like, what is the type name, what is the return type of this field, what are the interfaces that this type implements, and things like that. And so we don't actually do anything with the schema. And so we take this pre-built step, we create this, basically think of it as like an indexed, array that we know like, okay, this type bar is at this offset, and then we can go straight into it and like look it up. And we just load the entire thing. And so basically we cut out parse time for the server schema, and that is about like a 63% reduction in time cost per invocation, that's huge. It's a lot, and it's pretty cool. And so this was kind of one of the performance optimizations that we did to get even after we got it down to 5.5 seconds in Rust, to get it to be even faster. We got this pre-built flat buffer schema artifact. And also built with Buck. Everything is built with Buck. And yeah, that's kind of the end that kind of goes over the architecture of the native compiler, how everything fits together, and yeah. Any questions?
You showed up the Graphql refers package interfaces, but I'm assuming that does the provider also generate the network code to actually catch, like translate the catch?
It does, yeah. So there is a I guess that is one of the optimization processes that we do. Instead of like saving, instead of at runtime, instead of sending all like this text up for the server to parse and evaluate, at build time, actually one of the steps that the compiler will do is it will actually save to Facebook servers the content of all these queries for every particular build and every particular revision. And so you have basically a mapping query name to like a identifier for that query. And at runtime, what you do is you just provide that ID of, I want to execute food query, and that's ID 123, and then you provide all the variables. Graphql also has a mechanism where you can, like variables and things like that, which I kind of just glossed over. You provide the ID of the query, the variables for the query. The server will then just load whatever's been stored, execute it, and then return to the data. And the cool thing about GraphQL is, if you just go back to the very, very beginning here, the response is JSON. There's nothing like super particularly fancy about it. We do actually generate, not in this model generation pipeline that I talked about. There's kind of, this is really like the user-facing part of things. We do have another set of code generation like artifacts that are like infrastructure required. How do you get like it's called graph services. How do you get the graph services runtime to understand all these different things? And so we do generate kind of an artifact for it to understand this is what the response for this query is going to look like. This is where the fields are going to be, and kind of how it would parse it at runtime.
Do you also generate the models on the server side?
No, the server does not have models. The execution side of the server doesn't have models. There is there is JavaScript on like the client, but that's what Vila does, and that's still a client really. It's not the server necessarily. But yeah, there are models on the server.
Yeah, the schema is like derived from what the server does. So if you create a function on the back end and you annotate it with like, hey, this is first name on the user object, then you run the build step and that turns into like a user now has a schema, has a first name field.
Right, and the queries will be validated against whatever it is.
Yes, yeah. But like sort of the source of truth on the server is like, you just write some function and returns a string as your first name.
Yeah, you're basically writing the endpoints, you're annotating how should this be exposed to GraphQL, and then GraphQL server has their own, transpiler or annotation processors, whatever you want to call it, that will go through, parse everything, and then generate the GraphQL type schema from the resolvers that developers write.
I know that Rust edition 2021, I think just came out. Is there going to be issues like migrating this to that edition?
The new version of Rust? Not that I'm aware of.
We're already on it.
Yeah?
Yeah, that's what I heard.
Cool. So yeah.
Sounds like it works.
We haven't had any support quotes, so yeah, it's been working. Yeah.
So in the same vein, you mentioned that this used to be in JavaScript, and then you migrated it over to Rust. Can you talk about challenges taking an existing piece of existing infrastructure and taking it into this whole new Rust? What were the challenges in order to talk about how to face doing that?
Yeah. So the question was like the migration process, right? Like what challenges we face migrating this from JavaScript into Rust? I would say one of the biggest risks that we had prior to embarking on this project was like the GraphQL primitives, so like the GraphQL parser, writing all that stuff and making sure it worked, the AST, the IR. And so again, huge shout out to the Vila team, Robert and crew, who like de-risked a tremendous amount of work for us on that. And then from there, it was kind of like more so like some Facebook internals, right? How do we, like the deployment process was different. For JavaScript, we basically just ran source code from trunk. We would commit it to master, and then it would just execute. And we can't do that for this, and so we had to figure out the deployment process and like how all that stuff worked. In terms of the actual ports, I think correctness, right, was an issue, right? How do you make sure that the new compiler is generating the same output as the old one? And so we put up something about test frameworks and stuff to a lot of unit tests. That was one very cool thing about Rust as well. Kind of we have a test first culture now, because it's significantly easier to write tests that are just kind of lined up with your source code, and the language just makes it much easier than JavaScript and other languages that we've worked in the past. And so a lot of unit tests to make sure that the code works as expected. Just testing all of our edge cases, and then we had basically end-to-end tests to make sure that each compiler step would generate the same output. We basically diff the existing. We would run all the source code through the existing system, run all the source code through the new system. Does it produce the same thing? And then if it did, we would say this step is good to go, and then we report over the next one. But I think that was kind of like the bigger challenges there. Kind of the deployment process, which was very different, and then making sure that we didn't incorrectly generate artifacts. And it was good. We got this deployed to everyone in the company without them being much the wiser. Kind of like underneath them, things just kind of switched. And I think for us, that was the job well done. So that was really good. Yeah.
So one of the benefits of Rust that you guys are enjoying are memory management, right? Using the borrow checker, error messages, speed, which I guess compared to JavaScript is coming from the fact that you're using something that's interpreted in a virtual machine to something that's executed as a binary. So that's a large speed up, plus not parsing, using flat buffers. But are there any other features of Rust that helped in this? So, threading wasn't used, right, because you used another tool to parallelize it, because I guess there's no dependencies between parallelizing this binary, but like traits or any other language features that you thought were particularly useful in this use case?
Yeah, it was quite interesting actually that you mentioned traits. It's like jogging my memory a bit. The programming model, I think, between like Rust structs and traits is quite different than other traditional object-oriented languages. And so coming from like JavaScript, the way that we looked at interfaces and classes, and then trying to apply that, we ran into a little bit of a wall when we tried to just like directly apply the same structures that we had in JavaScript, just like re-implementing it in using a struct and a trait. Things didn't quite work out that nicely, and so it was a little bit of a kind of unlearning, or maybe like relearning how to do things the Rust way. What else? Some of the basic traits. I know like some of the really simple external traits that we used were struct.dot, super helpful, JSON, and then indoc. We use that aggressively for formatting the code and kind of like using it as a code template internally. Like all the models are written in indoc, macros and whatnot. What else? I mean, we do have some projects that we're working on at the moment that are using kind of parallel processing, so Tokyo and whatnot. But yeah, we kept it quiet and bare bones Rust for this portion at least. Yeah.
If somebody wants to change like a function on the server side, or maybe get rid of it because it's been there for too long, or they don't want to support it anymore, how would you handle that in terms of changing all the models, fixing everybody's code?
Yeah, it is a process, right? Because if you think about it, the server and the client code are not like very strictly coupled. I mean, they are to a certain degree because of the compiler, but you can think of the server as kind of declaring a bunch of server endpoints and fields and things like that. And there's nothing really stopping like a server developer from just going and like nuking the field and just like getting rid of it today. Even though there are production apps that are querying for it, or there could be even client-side code that expects that field to be there. The way that we do it today is we try to aggressively do it through tests, right? And so when you put up, there's a very I think sophisticated continuous integration platform at Facebook, and so when you put up a diff or like a change set that kind of will make this change, we will be like, hey, this is modifying this GraphQL field. You're like changing the type from like a string to an int, or you're getting rid of it, and then we will try to build the entire mobile app. We'll try to run out like the new schema. We'll try to run it through the compiler, see what happens. And if things don't work, then we'll throw a big red warning to like, hey man, this isn't safe. And then kind of at that point, the developer can either reach out to us and be like, hey, this is, I think it is safe. How do we kind of do this? Or they'll just kind of abandon that change set. But it's mostly enforced through unit tests at the moment. Yeah.
So coming from JavaScript, how ergonomic did you find Rust memory management? Were there places where you ended up having to put in like reference counting or cows or extra clones in order to get the memory management to work?
Yeah, I think, so we do have, like the schema and things like that are, are common. We don't want to have multiple copies of the schema in multiple places, but it's a huge object. We don't use a lot of refs and whatnot in our code. Things are mostly read-only until they get to a point where it's like, just take this this data that's in the AST and like, you then need to copy it over to like a Java, the class, you have to like actually generate the class out of it. And so, I think our rule of thumb is whenever we got, it took a while to like understand it, but then we're like, okay, cool, when you have like borrows and things that is like flowing, like there's a lot of data flow, right? And then when we had to explicitly got yelled at by the compilers, like, hey, you can't do this because, like use after borrow or something like that. And we would put in a clone. During diff review, we would be quite like particular on like, okay, why is there a clone here? Or like, is this actually necessary or things like that. But for the most part, I don't think it was that particularly challenging. JavaScript is like a wild west, you have no idea what's going on. I just like use it, something will happen, great. But I actually liked it. I like Rust a lot, right? Because you quite clearly knew how's the data flowing through the system, when is it going to be deallocated, if I'm going over like this other portion, it's just not going to be present, right? Like it took a little bit to understand it, but then once you kind of, I don't know, like once you start seeing the flow through the system, it's like, all right, cool, yeah, it makes sense.
The only question is the unsafe portion of Rust?
We did not use the unsafe portion, no. We stayed away from that very aggressively. Yeah.
Do you use the nightly compiler or the stable compiler?
Do you use the what?
Do you use nightly or stable?
Stable, yeah. Do we even have nightly available? Because it has to be, again, everything's built through Buck, and so whatever version, they kind of, we as a team can't really, we can, but it's like a lot more work to be like, hey, we want to use this version of the compiler. We just let that be managed by like Rust Foundation or like Buck. And then when they decide to upgrade us or do whatever, it just kind of comes as free for all of us. And so we use the stable version. I'm not entirely sure which version, but it is stable, not highly. Yeah.
Do you onboard a lot of new Rust programmers? How's that experience?
There's been a lot of interest for Rust at Facebook. I know there have been people who have specifically joined our team because we work on Rust. And so we have basically Rust at Facebook, we're like, hey, we're so-and-so team, Graphql native compiler team, we're working on this using Rust. Buck, like I was mentioning, they're also being rewritten in Rust. And there's all sorts of like, internal tools that we can rewritten in Rust. And so there's a lot of interest at the company for Rust.
Is there kind of a steep learning curve, or are people productive pretty quickly?
I think for the most part, people who come to us and like, hey, we want to work on Rust, they have some prior knowledge. It was funny because I think we would have been the ones who are like, we don't know really what we're doing. We're kind of like, this is we're JavaScript bros, and we're trying to learn Rust. But I mean, yeah, it's not. People say there's a huge steep learning curve. I personally did not think it was that bad, but I think it varies from person to person, and also the complexity of the code itself. And so I think that's one cool thing about ours is it's, there's not a lot of complicated stuff going on, and it's pretty like just bare bones Rust. And so if you want to come over for us, it's pretty easy to wrap up on, I would say. Yeah.
What kind of techniques do you use to ensure like the conditions that you just do in the last line of your compilation align with the validations that you were doing? Do you transform the IO as you go, or do you fuzz?
Okay, yeah, that's a great question. So the question, so paraphrasing it here, is how do we, after the validation pass, ensure that basically the data is still valid and we don't muck it up somewhere?
Or I guess you mentioned that in the final step, you have these assumptions that you made.
Mm-hmm.
If some assumption is broken, you can't count.
Yeah.
How do you ensure that all the assumptions in this final phase are broken checked repeatedly?
Yeah, so one is we have unit tests pretty aggressively for most of those assumptions, and so we'll have a test being like, we've made this assumption, and if the preconditions aren't met, we expect it to throw, and did it actually throw, or did it actually go mechanic somewhere else? Again, I think so the testing kind kind of the testing culture is very, very important for that. And then also, yeah, I think that's the biggest thing, because after we kind of do our passes and make sure that, okay, we've surfaced all validation issues to the user, if we internally like incorrectly build an app or do something else and we don't check against that, we just panic out later, and that's what we kind of surface to the user, like, hey, invariant not met, so this is line, whatever. We'll just throw like detailed error messages, and then that's when we'll kind of have to go back and as the maintainers look at what's going on. But that's kind of also our reliability metric. We don't want this to be going up, and so when we see things like that happen, we'll add more tests to make sure that this invariant is not hit again. Or kind of like this structure is always like in a safe state or like built properly.
What features would you add to Graphql spec?
What features would you add to Graphql spec?
What would you like to see in the Graphql?
That's great, man. Let's see. I think better variable support, right? Like variables, I spent a lot of this talk talking about the modularity of GraphQL, and GraphQL by its nature is not very modular. It's kind of like how we architect a compiler, how we architect the models out of it. And so just kind of bringing, I think, first class like library support to GraphQL, and variables, which I just didn't even mention, is a whole other mess, and just getting better variable support in GraphQL. Modular variables will work in GraphQL. That's what we want. Yeah.
I have another question about GraphQL generally. Like,
yeah.
if I have an app that's somewhat less complicated than the Facebook app, what is the real selling point for GraphQL?
Yeah. So I think. All right, hang on. Okay, a few things here, right? One is, as you can kind of see, right, like the query model and the response model are like very identical. They are verbatim actually, and so I think it's very easy for a developer to be like, hey, this is the data that I want, and fetch exactly that, right? If you look at traditional REST endpoints, or I don't even know what the other options are, but you go to like some obtuse endpoint and then you provide some parameters and it'll return to you a bunch of data, half of which you might not even use, right? And so as a developer, I need to then keep it very much in sync, like, okay, what is this endpoint continuously going to return to me? Here, we know if the schema is defined to be this, I know any of the response looks like this, and your clients are going to only get the data they ask for, right? If I go to a REST endpoint, unless you have like filter parameters, you will most likely be returning, there's two ways it can go, right? You can either have one endpoint that returns a lot of data and have a bunch of filters, or you have a bunch of smaller endpoints where you can go and fetch a bunch of different things. It's a lot of like back and forth. So your size over network will also be significantly smaller in theory. And then there's more features of GraphQL that I didn't really talk about here, but you can actually fetch multiple blocks of data in the same request, just by the nature of how the language is structured. A really good example is, I want to find, let's take a Facebook example, right? I want to find all the events that I'm going to, and then all the friends that go to those events. I can write that as a single GraphQL query that will be validated once on the server, and the data will just be sent back to me. But depending on how your REST endpoint is structured, you will have to do multiple round trips, right? You'll have to do one request for events, get all those back, and then take all those IDs and like show me all my friends, and do another request and get all the data back. And so you can actually eliminate a bunch of round trips on how the GraphQL type schema is defined.
But overall, like, because I don't quite know how this is implemented on the server side, but you have these resolvers, right?
Yeah.
That's, will like give you back some block. I'm wondering, like, for smaller apps, whether it's worth writing the resolver and the GraphQL endpoints, and like on the client side, the GraphQL like interpreter and everything. Like,
yeah.
Is it really simpler?
I would say one thing, right? So the resolver on the endpoint on the server is just one. There should be like, there's just one GraphQL endpoint that handles everything. It just takes in a query and will give you data back.
But you still need the resolvers, right?
Yeah.
Like for every data source.
But I think the counter argument there is you're gonna have to write that resolver anyway, right? You would have to write a resolver for your endpoint, it's like your endpoint controller, or it's the resolver for the field, right? So I can either write the endpoints kind of controller that goes and queries my SQL database and then exposes this JSON object, Or I can write the events object controller resolver that is bound to this type in the GraphQL schema, and then the GraphQL server, when it goes through and parses everything, it executes everything, all right, we'll call this function for this object, and then it would do the same work. And some of the really cool things is that there are a lot of open source implementations of GraphQL servers and GraphQL clients, and so you don't have to write a lot of the boilerplate stuff. The server would, you basically write your resolvers, bind them to these fields, and then the server just handle the execution logic for you. And then on the client as well, you don't even need to have, a lot of the stuff that we do is for strong type safety, but you can just honestly just parse it. I mean, if you want to be super basic, that's what is happening for a REST endpoint right now anyway, right? And so I think you don't have to go all in basic is what I'm trying to say. You can start with a little bit. You can actually have GraphQL intermixed with another data source. You can have it REST or whatever. But yeah, I think it's super cool. And it works out really well.
Thanks.